Now, next thing we want to do, let's just try to make test analysis. What we want to figure out, the kind of relationship between, for example, mile per gallon and the engine. So is there a relationship between them? If you remember, we could come to the scatter plot, and in the maybe the axis, we will put the engine, and then the mile per gallon will put the Y. Obviously, when I start to look directly, if I want to put a line just to see the kind of line here, if you want also to smooth the line, put normal line, but it is obvious it is a negative kind of relation. So for some times, the engine size was in an effect, seems to be at this time, the size of the engine had quite a bit, not a clear, it's a constant. I mean, the mile per gallon was increasing over the time when the engine size was. But once the engine size from, like, say, above 100 started to change, when you put the engine size, the mile per gallon started to go down. So you could see from somewhere around here, it is a negative relationship. So the larger the engine, the less mile per gallon you could go. So the less efficient the car is. Let's try to measure against the horsepower. Once again, you have a negative relation somehow around starting from here. This is again not linear. When we do prediction from the start to the end in the next book, we will see how can we construct a line that is not linear, because it's not a linear relation, obviously now. The larger the horsepower, the less mile per gallon could go. Acceleration as well. It seems to me a really weak relation between the acceleration and the mile per gallon. They don't seems to be really correlated to explain the differences. Now, to prove all what we are trying to speculate from imaging, we're going to use tests. Now, these are what are the descriptive analyses. Before I do the test, I want to show you, if I go to regression here and try to correlation matrix, right, between these variables that we just checked, the continuous one, to actually check also the experiment correlation Pearson. I think the difference we spoke before, one of them, the assumption of normality is important in the person, but the experiment, assuming that they are not normally distributed. So we're going to bring both of them side by side to figure it out. And the plot of the correlation matrix, let's see what the plot looks like. This is a symmetric table, right? This is the mile per gallon and against the engine, which is negative. We saw it. And if you want to look at the relation between them, it is minus 7.8. Next thing, we check the mile per gallon against the horsepower, right? Again, mile per gallon against the horsepower, it is negative and seems to be minus 70. If you look at the engine size with the horsepower, they are positive. So the larger the horsepower, the larger the engine, strongly correlated. Then you look at the mile per gallon gain against the weight. Negative relationship is obvious with this. The engine against the weight, which is in here, wow, they're strongly correlated. 93% correlation. That's why you can see it's almost perfectly with together, right? And by the way, if you want to read this, this is the Pearson experiment ratio, which is not too much far from each other, because some of them, the distribution was okay. For example, here's minus 80 and the experiment test minus 86. So it's a marginal of difference. Next thing I want to do now, the test, according to my hypothetical. Is this what we are reading happened by chance, or it is real, representative of the real population? What I want to show you is the t-test. Now, in the t-test, we know the difference between these three different scenarios, whether a hypothesized value, a paired or independent from two different groups. So let's check the paired one that is a subject with two different groups. Now, if I would have to take the mile per gallon, all right, and against the engine and see the difference between their means. If you remember what was the sample test of T, say like, okay, I want to test the difference between the mean of the mile per gallon against the mean of the engine. Now the question, is this a right test? No, it isn't, because it's completely illogical to check the mile per gallon test. Let me just bring the descriptor to show you what I mean. You see the mean here the mile per gallon, the range, is completely different from the average range of the engine size in inches. That's why it's 23 and 192. Of course, they are different. That's why it shows a significant difference. So this is a wrong test. That's why I said learning about the statistics, you have to visualize, you have to understand the purpose for the test instead of just utilizing, snapping that into the program, because the program is not intelligent to tell you you're using a wrong logic. So I hope this is a good example for you to let you understand the difference, because the means between these guys are completely different from each other. But imagine if I want to compare a group, like different group on a certain mile per gallon, this can be a right one. So what I want to do, when I come here to the independent test, and I want to say the mile per gallon, I want to investigate it in terms of a grouping variable. But look what will happen when I bring the origin. Now, don't forget the origin, as we said, there are three. Now, if I want to bring this and grouping the variable, I should see having a problem here. What is it saying me? Must have 211, because this is a t-test. And we said when we have a grouping variable, this one happens to be ordinal. With more than 2, then we are using the wrong test, should be the ANOVA, because we have more than 2 groups. So to this test, this is not right test to do that, not the t-test. It should be only 2 groups. Let me show you. For example, we have the filter. If you remember, like some car will be selected, others will not. If I want to bring this, because there are 2, it's possible now. Now, what he is telling me, turns out the mile per gallon, in terms of the 2 groups, the cars they've been selected, the cars will not been selected, is significant. It means that they are not the same. So the group of the car that been selected, their mean, in terms of mile per gallon, differ from the mean of the cars they have not been selected. If you want to see the mean difference, you can add here, and you could see the mean difference happen to be in a minus. I mean, imagine this is an absolute value. The standard deviation is almost close to 1 standard deviation. You could see the effect size as well. He used the Cohen's the effect size. It's a quite large one in a negative way. Now, maybe I want to bring this one a little bit. Look here, the number of the cars. Now, they were not selected 102. They were 288. Well, quite the sample number between the 2 groups are quite different. One of them is like twice as the other, but look at the mean difference. Now, the car that were not selected, they were just like 15 miles per gallon, but they were selected at 26 miles per gallon. So that means the car that was selected are better than the other. And so quite obviously right things to think about it. Now, if you want to check also the descriptive plot, could see the difference of the mean between the 2 groups, right? So I hope now this test, it makes quite sense, especially when it comes to using a t-test sample of an independent one. I'm going to use ANOVA test. Now, if you remember, we have like one-way ANOVA, right? And the ANOVA and repeated measures for ANOVA. Then we have the Anakova or the Manakova, and non-parametric for one ANOVA, the Kroskal Welles. Now I'm going to bring back my table. Now in this table, when we reach out that we have 2 or more samples, for example, let's look at the origin of the car. We got 3. Now the question is, are they independent or dependent? They are independent because 3 different groups. We are not measuring, like, for example, on the same subject, the 3 different values, but we are measuring 3 different groups. So we are here. And now what we are measuring, it is a continuous value, which is mile per gallon. And we are measuring either the mean of the variance. Of course, we're going to look at the mean. Now, we're going to use 1 factor, 2 factors, or larger than 2 factors. So let's focus on either we're going to look at 1 factor or 2 factors. So we're going to use ANOVA 1. It's one-way ANOVA without repeat measures. Now, if it happens to be dependent, we will be using ANOVA with the repeat measures. So we're going to go to ANOVA. There's one called one-way ANOVA. So what happens? We want to bring the mile per gallon. It will origin 3 different groups. So this is the 3 groups. Now what he say? The 3 different manufacturers, they have different mean on the mile per gallon. And it is significant. They are not the same. So the 3 manufacturers, they differ. So we want to find out how. This is a descriptive table here. You could look at the difference mean. Now, the mean for the Americans happens to be 20 miles. This is 30 miles for Japanese. We saw this before. We saw it. Now we want to look at the table. That could be greatly obvious that they're really different. So the less want to go mile per gallon is the American manufacturing car, and the winner could be the Japanese kind of car. Now, one more thing, it's about the assumption. Now, perhaps in the discussion we didn't really go details into how to do the ANOVA test from technical aspect, but one thing it's offered is called the homogeneity test, and that's one assumption quite important. And what does this assumption says? It requires that the variance between the groups, the variance between the three groups, it should be equal. This is in order to do the right ANOVA. So if the variance between the three groups is not equal, it means the ANOVA test will not give you the right result. Let me show you exactly what I mean. The assumption of homogeneity says that I want this sigma square of the first group should be equal sigma square, second group should be equal to the sigma square of the K group. All right, this is my null hypothesis. The alternative hypothesis says, well, at least one of them, it is not equal to the sigma square K, at least one of them. Now, when I do the F test, what I wish for, now, the F test, as we said, will spell out a value. Now, in order for ANOVA to work, what I want the null hypothesis to be true. Equal variance between the three groups. So the variance between the three groups should be equal. So I hope to get a value that is larger than the 0.05 if I am constructing on 95% confidence. If it happens to be less, then this ANOVA is not going to work. Now, when we use the homogeneity Levine test, what is the p-value happens to be? It is 0.90. This is way bigger than 0.05. So in this case, the null hypothesis, I fail to reject it. That means the variance are equally distributed. That's why the ANOVA result is accurate here. I can consider it. And this is quite obvious from the graph as well. Now I'm going to use this ANOVA alone, see the difference between them. One important thing you can get from this, different from the other one here, we did ANOVA, one-way ANOVA. With this ANOVA, that we can get something called partial theta square. And partial theta square, it is a test. It's telling you by how much differentiation these three groups, the MyPer is accounting for the difference between them in terms of the mean, maybe at the medium size. 33% of the variation in the mean between the three manufacturers is accounted by the mile per gallon. If you'd like to say also maybe the horsepower, you could see like 24, it's less. It's still significantly difference between three of them, but still less. But let's check something important is about the assumption to make sure we are doing correct. You see, this is an important. This is not accurate result because when I bring the origin, I expected the Levine test to be not significant. Here is telling me the variance between them in terms of the horsepower are significant. So to this end, I cannot rely on this test. So let's take this back. Let's try to take the weight. See, the weight again is not correct. Let's try to take the acceleration, just like see the difference. Well, this is even worse. So the only one was fit to do the ANOVA. It was the actual mile per gallon. But let me show you the test of one-way ANOVA again, the Kroskal-Wallis. Now, since we have violated the assumption, let me bring you to the map. The Kroskal-Wallis, if you remember, it is to test the median in this case, or the value that is not sensitive to violation of normality. Now I'm going to go to Kroskal. It's a non-parametric, as we said. Let's try to take the mile per gallon again, just like for checking out. Check the group. Again, it's significant, as we said, and the effect size exactly the same as we did before. But look now, the difference. Now, when we bring the engine, which failed to do with ANOVA, but we bring it here, now it makes quite a bit sense. Now, what he says here, it says, yes, actually, in terms of the engine, they are different from each other. Now, if you want to prove this correctly, let's go to descriptive, bring the engine, and let's split them by the origin, as we did before. I'm going to bring the histogram and box plot. Watch carefully here. It's quite obvious they are really different, right? Especially when it comes to the American car's engine, quite different from the European one. The European Japanese way below the size of the engine of the American's car. The mean average of the American cars, it goes with the engine of around 248 in comparison to the European 109, 103. So the result we've got in here, test of non-parametric cross-scale, was quite obvious, and it's 51% that there can be difference. If you like to do the ANCOVA, listing this and the factors to be the origin, it is the same as we got it before in an ANCOVA. But the only difference here is saying that the difference between the three groups, the correlation between them is significant. This is what we expect to get, but I want to see the assumption here one more time. Yes, we're good with the assumption, it says the same, but I want to bring here the origin. Now here in the estimated marginal means, this is the same plot we did between the Americans, European, and Japanese car, and you can see the European, Japanese, they overlapped, and the American, they didn't. So the analysis of covariance between the three different groups is quite significantly different from each other. Last, maybe if you like, we did the independent test of contingency table, of just to show you an example of the origin of the car. Let's put them in the road and a kind of cylinders here. So what you can see that the different cylinders, the manufacture of cylinders, according to the three groups, they're significant because we reject the null hypothesis. They are the same. So they are not the same. If you want to look at the count, it's quite obvious by looking at the cylinder 8 for the American cars, the larger cylinder than the others. So Japanese and European, they didn't use 8 cylinders. But most likely they were focusing on the 4 cylinders. But maybe the bar plot is what I wanted to do. It's obvious by looking at different kind of cylinder, 3, 4, 5, 6, and 8. Look at the Americans. I mean, the only focused of them is the 8 cylinders, the highest, and then you get the green, the 6 cylinders, and then you get the 4 cylinders. But the 3 is not there, 5 is not there. But you could see that the European and Japanese are focused much more on the 4 cylinders. So that was all about this data set. We've explored the univariate, bivariate, multivariate as well. So let's go ahead and for extra work to explore a second data set. I'm going to use the built-in data set comes with JAMOVI as it. And this is the bugs data set. I will see you then.